Okay, you're going to need to have a printout of those notes that I put on the teacher page, which is just this picture. So actually, singular note, just this picture. Okay. So the homework for tonight is to listen to this screencast carefully, take the requisite notes, and then come to class tomorrow ready to work on this. All right. So there's no work tonight other than you taking this screencast down. I will kind of do a verbal touch base with you tomorrow to see how well you did listen to this. Okay. All right, so what we're going to do today in this screencast is derive how to find the length of a curve over an interval. There's a couple of terms you want to know. Arc length, when you're asked for arc length of a curve, arc length is synonymous with length of a curve. So if you look at this picture here, the red is the function. I'll talk about the demarcations in blue in a second. But the arc length from x equals a to x equals b is synonymous with saying the length of the curve from f of x, which is the f of x here, from x equals a to x equals b. I'm going to go now and start deriving this formula. What's drawn in this picture, which is really nice, is they've kind of made some rectangular partitions here, and they just called these P1, P2, P3. What I'm going to do here is just kind of draw the vertical drop for a second. Okay, you'll notice in this picture, and this is one I just found on the internet. I mean, I didn't make this one. You'll notice here that, let's see, is delta x. I think they intended for delta x to be constant. It looks to be that way at least. Okay, and what I'm going to do here to derive this, I'm going to take one particular segment right here, this interval, and just kind of zoom in. And when I zoom in, I'm here. Okay, so I've zoomed into this one segment, and just remind yourself here, the red is the actual length of the curve. Okay, the red's the length of the curve. This blue here is the blue up here. So what this person did here was, when they had this curve, they just kind of found points at certain equidistant distance horizontally on this curve, and they connected these points with straight line segments. Okay, straight line segments. All right, let's come back here. So we're zoomed in on some subinterval. We'll call this the kth subinterval. And what I'm going to show you here is that I'm going to superimpose a right triangle here. Because if I can get an expression for the length of the segment of the, if I can get an expression for the length of the portion of the function of x, right? I think you can see where we're going here. The length of the total function of the curve from x equals a to x equals b would just be a summation of each of the individual subcurves, if you will. All right, what I've done here is I have superimposed a right triangle whose hypotenuse then would kind of coincide with that blue segment, okay? And I'm going to call the horizontal distance here a change in x. I'm going to call the vertical change in here a change in y. And I'm going to call the hypotenuse h. And what I'm going to do here is I'm going to actually call the length of the curve, the actual length of the curve s, okay? And as you can imagine in the picture above, there are, let's see, 1, 2, 3, 4, 9 subintervals. But you can imagine that as the number of subintervals increases, these kind of rectangular subintervals squeeze together, these segment points squeeze together, and what you probably see here is that as delta x gets smaller and smaller and smaller and smaller and smaller, as delta x approaches 0, h, the hypotenuse, approaches the actual length of the arc s. Okay, and so let's kind of do this out. Well, we know from the Pythagorean theorem that delta x quantity squared plus delta y quantity squared equals h squared. I'm going to now just solve this for h. H equals the square root of delta x squared plus delta y squared. Now I'm going to do some fast algebra. I'm going to factor delta x squared out of these two terms. Look over here. I factor delta x squared out of delta x squared, and I factor delta x squared out of delta y squared, which means this term, right? This term, when I factor delta x squared out, I'm left with a delta x squared in the denominator. Now, if I have delta x squared times something, and it's square root of the whole thing, delta x squared can come out and become a delta x, and now I'm here, okay? Now look at this expression for h. H equals delta x times the square root of 1 plus the quantity delta y over delta x squared. As we said above, as delta x approaches 0, h approaches s. Delta x approaching 0, when we say delta x, or the change in x approaches 0, we want to have a symbol for a really, 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 really small change in x. And we do. Dx means a really, really, really small change in x. And if delta x is getting smaller, look at the picture. If delta x gets smaller, if this whole thing squeezes in, delta x gets smaller, but then also so does delta y. Hi, how are you? Hang on a second. Yeah, I'm doing a screencast here. As delta x approaches 0, delta y will also approach 0. And luckily, we do have a symbol for a really, really, really small change in y. Okay? If delta x approaches 0, that means delta x is getting closer to dx, and delta y over delta x is just approaching dy over dx. This here, we don't really talk about that often, but we have to remember that dy just means a really, really, really small change in y. Dx just means a really, really, really small change in x. And dy dx, hopefully you recognize another way of writing f prime of x. So if you go back here, so h, after all that work, h actually equals, look at these two. Look at these two. H is equal to delta x, here's delta x, times the square root of 1 plus f prime of x, where f prime is squared, okay? This here gives you the length of one of the subcurves, but as delta x approaches 0, how many subcurves are we adding up? An infinite number of them, and whenever we add up an infinite number of things, we know we're going to have a definite integral. And here's where we are. At the end of the day, the arc length of a function of x over some interval of x from a to b is the definite integral from a to b of the square root of 1 plus f prime of x, where f prime is squared dx. To use this, something you have to remember that does not get emphasized enough is that f of x, the curve that you're trying to find the length of, it has to be differentiable over x, okay, over the interval of x, because, let's take a look at understanding why. Because if you think about this whole right triangle relationship that we can kind of impose here is only true if you don't have a point of non-differentiability. So look over here. If I look at this function f of x, and if I wanted to find the length of the curve from 2 to 11, for example, okay, there's a point of non-differentiability here, which means if I was thinking of the kth subinterval, okay, whoops, something just happened. How do I go forward? I don't know. What just happened? Let's see. Oh no. Okay, so which means if I was looking at this subinterval here, for example, okay, that right triangle relationship, right? If I was looking at this subinterval and I made a line segment, like there's no, that right triangle relationship fails me, okay? So if your function f of x is not differentiable over the interval of a to b, what you have to do is then use two integrals to get the arc length from 2 to 11. One integral will be from 2 to whatever this point is, and then you have to add the integral from 2 to 11, okay? All right, I know some of you thought to yourself, oh wait, but here it looked like that could have been a triangle. That is absolutely not the point I'm making. The point is that the whole point of this derivation here is that when you connect with a line segment, as delta x gets smaller and smaller and smaller, h approaches the actual length s. You clearly see here, that this is h, so to speak. This hypotenuse is h, and then look at s. S is here.
h never approaches s in this situation, okay? So to use this formula for arc length, your function has to be differentiable. Also, in the middle of preparing this screencast, I happened to find this little graphic on the internet, which is, I think, kind of nice. Same exact thing. They just kind of drew in like a representative hypotenuse, kind of like this phrase, the minute section of the curve, which just means like one particular segment zoomed in. But anyway, all right. Final thought, final point of contention here is that what if the curve we're looking at is a function of y? I gave you a picture right here. So let's say I have a function of y, and I want to find the length of this curve from this point to this point. Okay, and maybe I'll ask you, like, what do you know of the endpoints of this curve? Well, this occurs at y equals 0. Okay, what's this one, everyone? Yes, that occurs at y equals 3 pi over 2. So what's interesting here is, let's go back to this expression. The dummy, again, has to agree with everything. If you're looking at the length of a function of x, then it makes sense, hopefully, that the dummy has to be x. If you're looking at a length of a function of x, then the limits of integration have to be x equals. Okay, and of course, if you're looking at the length of f of x, then the integrand should be in terms of f. Here, in this case, what we have here, this curve, it is not a function of x, but I can call this, look at my notation, I'm going to call this a function of y, or g of y, okay? And if I want the length of this function of y, the arc length here is going to be, and sometimes texts use the word capital L for arc length, it's going to be, let's see, a definite integral in terms of y. And the limits of integration, I'm going to call this c to d. I'm going to add this, though. It has to be y equals something to y equals something. And what do you think the integrand is going to be? It's going to be the square root of 1 plus g prime of y squared. So if I were to ask you to describe the length of this curve with an integral expression, you would do the following. Okay, actually, you know what? Why don't you go ahead and do it on your own, then play me for the answer. All right, well, the length of this curve, that length L, is going to be the definite integral from 0 to 3 pi over 2 of the square root of dy, 1 plus g prime of y squared. Well, let's see. This, I have to rewrite this as actually a function of y. X equals sine y. Okay, now this is actually a function of y. So the fact that I actually wrote equals g of y here is actually a righto technically, because the way I've expressed it here has not been solved for x. But anyway, okay, now let's take a look at this. Look at this. dx dy is cosine y. This is the same thing as g prime of y. I'm taking the derivative with respect to y, okay? And now g prime of y squared would be cosine squared y. So this is my integrand, okay? This whole idea of g prime of y is kind of new for us. All that means is we're now just switching the roles of x and y, all right? All right, I'll see you tomorrow with this information so that we can then begin using it with some examples. And then what I'll also do is tie this topic of arc length to finding the length of a curve that's defined parametrically. So I will see you tomorrow.